Now, we've looked at equivalent fractions as fraction models. We've looked at equivalent fractions as dots on a number line. Now we're going to just look at equivalent fractions and see if we can utilize the patterns that we found in those other two topics. Let's go. So notice that this problem is not giving any kind of a setup. It's not providing any sort of diagram. It's not providing any sort of instruction on how to go about this. That doesn't mean, though, that students can't utilize what they learned previously. I think they should continue to draw probably these rectangles. I like these rectangles that we've been using. Let's see if I can make two that are roughly the same size. Almost. Close enough. And if one of them is split into 4, and one of them is split into 8, then 4/8, 1, 2, 3, 4, would be how many fourths? How many of these eighths is equivalent to how many of those fourths up top? And once you look at it, it's hopefully pretty clear that the answer is 2 fourths, 2 out of 4. However, once again, once your student begins to see the patterns behind this, they can sort of step away from the models. They can sort of step away from the diagrams and begin using the patterns on their own. Again, this is not the same thing as memorizing a formula. This is understanding what these fractions represent on a fundamental level so that you can do calculations with them abstractly. Two fourths. Same deal here. If I were a fourth grade teacher, at some point I would start talking about multiplication. Hey, look, have you noticed that in all of these equivalent fractions, it seems like the top and the bottom are multiples of the original fraction? So if we're doubling the top, then we're doubling the bottom. And again, that should make sense from an intuitive perspective as well. If we are doubling how many pieces there are, then each piece must necessarily be exactly half of the size. 1/3 is 2 out of 6. Similarly, 30 out of 100 is the same as 3 out of 10. This is a great example to show folks, if they are still sort of stuck using the diagrams, you can start to say, well, do you really want to look at a diagram that has 100 pieces in it? Abstraction is useful because it allows us to think in larger numbers than just up to, I don't know, what, a 10th or a 12th might be as high as I would want to go if I was drawing my own diagrams. 3 over blank equals 9 over 12. At some point, once they get the pattern down, your students should start being able to move through these pretty quickly. It might take time, it might take patience, and that's okay. But once they get the pattern down, hopefully it will stay with them because it will be used over and over and over again throughout their mathematical career. That would be 3/4 is 9 over 12. Same deal. It looks like we're tripling the bottom number, right? 4 times 3 is 12. So we're going to triple the top number. 1 times 3 is 3. 3/12 is the same thing as 1/4. Again, looks like we're doubling this time. We're taking the number of pieces and doubling it. So each piece is going to be half the size that it originally was. So instead of 3/4, we have 6/8. And finally, what number could replace r below 3/4? I think we just said this, is 6/8. Excellent work. Let's keep going.